In this video, we're going to review finding Thevenin equivalent circuits. We'll also relate the act of finding Thevenin circuits to a graphical representation of the current voltage relationship of a linear circuit, which is called creatively an IV plot. I've brought the circuit we analyzed in the previous video over to this slide. We're now very capable of solving this circuit, which, by the way, means finding every voltage and at every node and every current in every branch, either using matrix math or by using standard node-by-node circuit analysis techniques. But just because we know what's going on inside of a circuit doesn't mean we know everything interesting about it. Ultimately, we're going to want this circuit to interact with the rest of the world, either by hooking it to another circuit or to some transducer that cares about the voltage and current it provides. And we represent that connection to the rest of the world using a port. When we're analyzing the behavior of this circuit at a port, we'd like to abstract away the details of its operation. And we can take advantage of the fact that we are looking at a port to do so. If we can find a relationship between port voltage and port current, then whatever we're connecting to the circuit can just use that port IV relationship instead of representing the whole circuit. This graph shows a relationship between port voltage and port current. And we know that it does so because every element in the circuit is linear. So the port voltage and port current relationship must also be linear. If I were to increase V port by some amount, there's no element in this circuit that would cause I port to respond to that increase in a nonlinear way. That's neat, and it lets us simplify our representation down to a few kind of key measurements, which I've included on this plot. The x-intercept is called the open circuit voltage, and it's labeled VOC. This is because open circuits have no current running through them. So if you connected an open circuit to the port, you'd have a port current of 0, a port volt, and a port voltage of the x-intercept. The y-intercept is called the short circuit current and labeled ISC. That's because short circuits have 0 voltage across them. So if you connected a short across the port terminals, you'd have a port voltage of 0 volts and a port current of the y-intercept. The slope of the line is named after a special resistance called the Thevenin resistance. But the slope isn't exactly equal to the Thevenin resistance. In fact, it's 1 over RTH, the symbol commonly assigned to the Thevenin resistance. And that's because the rise over run on this plot would have units of amps per volt, which is the inverse of resistance. We can make a representation of this graph using a simple circuit. Either the Thevenin equivalent, which is pictured on the top of this slide, or the Norton equivalent, which is pictured on the bottom. I think it's particularly clear how the Norton equivalent relates to the graph because it directly implements the slope-intercept form of the IV relationship for the port. So here we're saying I port is equal to the intercept, the short circuit current, plus the slope, 1 over RTH, times the x value, V port. I'd like you to pause the video and find the Thevenin resistance for this circuit in 2 different ways. One way is to very directly find the rise over run of the line that represents the port relationship for this circuit. 2 convenient points that you could use to calculate rise and run are the short circuit current and the open circuit voltage. And I've found those 2 values by connecting either an open circuit across the port or a short circuit across the port and then using superposition. Calculating the ratio turns into some messy math, so I didn't follow through with it for this video, However, this calculation technique can be very useful when you have measured values of the short circuit current or the open circuit current in the lab. You can just have two numbers that you divide. Now, as a side note, you'll do a lot of algebra when you're learning analog design, and I'm trusting you as learners to go through the steps of that algebra by yourself when you need to. I'm going to vary the level of detail I show in algebra in order to highlight important concepts or common techniques, but you should always feel free to pause the video and work some algebra out for yourself if you want confirmation. A much faster way of finding the Thevenin resistance is zeroing out all the sources in the circuit and then calculating the equivalent resistance seen by the port. I've drawn a copy of the circuit with the sources zeroed that makes the current source open and the voltage source short. And then I've used that copy to calculate the equivalent resistance. So this algorithm is great, it gets us to a Thevenin resistance, but it seems just as magical as superposition. The reasoning behind it, though, is anchored in the linear IV curve we just saw on the previous slide. This curve can be reduced to a slope-intercept form, and we know that the intercept has to be created by power sources, so current sources and voltage sources, because all of the resistors in the circuit have a property called passivity. That means that when you apply zero voltage, you get zero current out of them. They don't generate power. So if we zero out all the power sources in a circuit, then we can't have any intercept, but the slope remains unchanged. So we can calculate the slope very directly. Also, as one quick definition, I told you partial definition for passivity, which is zero voltage for zero current. Technically, a circuit element is passive if it exists only in quadrants 1 and 3 on the IV plane. That means that it produces no power when zero voltage is applied, and power is dissipated in it in the first and third quadrants. If an IV curve passes through quadrants 2 or 4, then it's technically generating power, which means it's no longer passive. There's one other way to calculate Thevenin resistance that you might not have been explicitly taught, which is applying a test source. As a preview of how this method works, the mathematical analog to solving a circuit with a test source is taking a derivative. So that's different than like the rise over run or the slope intercept techniques that we used on the last page. Keep that in mind as we start talking about the test sources. Test sources are differentially small voltage sources that you attach to a voltage or current sources that you attach to a port. You apply a differentially small signal to a port, either a voltage or a current, using that source, and that sets one of your two port variables. You can then calculate the other port variable, for example, finding V port if you apply a test I port, and then you use that second variable to find RTH by taking the ratio of it with your test variable. When you do this analysis, you need to shut off supplies because they don't undergo differentially small changes. It doesn't matter if the values in a circuit underwent a tiny shift, a voltage source will still always have V across it, and a current source will still always have I through it. And I often summarize that behavior as saying voltage sources are where little wiggles go to die, so they don't ever change their values. You may notice that shutting off the supplies and calculating the voltage produced by a test current is identical to the slope-intercept method on the last slide, and that's true for resistor networks. We're going to start looking at things that aren't resistor networks later, and this test source is going to prove itself to be a useful way to calculate Thevenin resistance of those. One other detail that may prove useful later is that your choice of whether to apply a test current or a test voltage can sometimes be very tactical. It can make the math much easier if you pick the proper one. So, Thevenin resistance and open circuit voltages are great ways to represent circuits with one port, but there are a lot of circuit elements in the world that have two ports. I'd like you to pause the video and see if you can write down a few two-port circuits. And as a hint, think about circuits that either have both an input and an output, or that have like two ends. Some of the examples that I came up with include coaxial cables, resistor dividers, amplifiers, transformers, and this crazy mutation of the circuit we've been looking at, which now has a second port bolted onto it. The box I've drawn around this circuit indicates what the two-port abstraction is trying to hide from the world. Just like a Thevenin hides all the details of a one-port circuit, the two-port representation would hide everything inside of this box and reduce it just to its port behavior. There are a lot of interesting things I could say about two ports, but we're going to skip almost all of them in this class. My RF class delves into this topic much more deeply, so take that if you're curious. One detail that's worth mentioning is that two ports don't have just one value of RTH, because two ports describe the relationship among four variables, vport 1, iport 1, vport 2, and iport 2, which requires more numbers to summarize. You can't talk about the relationship between those four with just a single number. Another fact that's worth mentioning is that two-port theory only works for linear and passive circuits, so the circuit that I actually have drawn on this slide isn't a good candidate for two-port analysis because it's not passive. And finally, one thing to remember about two ports is in general they are bilateral, so things that happen on port 1 can affect the variables on port 2, and vice versa. Things that happen on port 2 can affect the variables on port 1. So even if you're only measuring port 1, things that are connected to port 2 can change your measurement. That last detail is really important because we're going to mostly ignore two-port networks in this class by terminating them, by connecting a resistor across one of the ports. Once you have terminated port 2, this whole circuit now only has one port on it and starts to just look like a one port that can be described with a Thevenin resistance. However, when we start measuring things that have two ports, you have to be very careful to pick a proper termination here so that bilaterality doesn't mess with your measurements. So put a pin in that. We'll come back to it when we start measuring amplifiers. In summary, Thevenin and Norton circuits are linear replacements for circuits and that equivalently capture their port behavior. You can find the Thevenin resistance by shutting off all of the sources and calculating the equivalent resistance, or by using test sources. In this class, we'll always turn two ports into one ports by terminating one port.